Hello, first of all, I would like to thank the organizing committee and Sergey in particular to giving me the possibility to present our recent results at the third virtual European Polymer Conference. Our results concern double dynamic networks based on entangled worm-like micellar chains and cross-linked polymer. This work was done in Russia at Moscow State University. Many surfactants are able to form a so-called worm-like surfactant micelles. These micelles are enormously long. Their lengths can reach several tenths of micrometers. Here you can see the micrograph obtained by cryo-TEM electron microscopy, and you can see how these worm-like surfactant micelles look like. Similar to polymeric chains, those micelles can entangle with each other, forming physical networks that exhibit viscoelastic behavior. As micellar chains are formed by weak non-covalent interactions, they incessantly break and recombine. And this makes the viscoelastic properties of those surfactants highly responsive to various external factors like temperature, additives, and so on. The most important among these properties is the responsiveness of micellar networks to hydrocarbons. Addition of N-heptane or N-decane leads to a huge drop of viscosity by 5 orders of magnitude. The effect is quite spectacular. Before the addition of hydrocarbon, we have a gel-like system. You can see the vial which is put on its head, and the system doesn't flow. When we add just few drops of hydrocarbon, the gel instantaneously transforms to a fluid with low viscosity, close to that of pure water. This effect is due to the absorption of hydrocarbon in the hydrophobic core of micelles, and this leads to the transformation of cylindrical micelles into microemulsion droplets. Breaking of cylindrical micelles leads to the disruption of the whole network. The ability of micellar networks to be completely destroyed by hydrocarbons is a peculiar property of micellar gels. It is not observed in ordinary polymer hydrogels. And this important property allows the application of micellar gels in oil recovery. In this field, these gels are used for the creation of an artificial medium with high permeability with respect to oil. This artificial medium represents the suspension of so-called propant particles. These are sand or ceramic particles in highly viscous medium. So we have a gel of entangled worm-like micelles where these particles are suspended. And this represents an artificial medium with high permeability with respect to oil, because when oil is pumped, the gel is destroyed and oil can flow freely between these loosely packed propant particles. But the drawback of this micellar network is that then they can be rather weak. And therefore, for those applications, they should be reinforced. The aim of our work was to elaborate the approach to reinforce the micellar networks by polymer chains, whereas keeping the precious property of this micellar network, the responsiveness to hydrocarbons. Previously, for this aim, mainly macromolecules interacting with worm-like micelles were used. For instance, it was proposed, for instance, it was proposed to use hydrophilic polymer with hydrophobic side chains. Such polymer can interact with worm-like micelles by incorporating its hydrophobic side chains into the micellar interior. As a result, a common network is formed where some subchains are composed of worm-like micelles, whereas other subchains are formed by polymer. And at cross-links, the hydrophobic side groups of polymer are penetrating in the micellar interior. This system was quite interesting. It showed a very strong increase of viscosity upon mixing polymer and surfactant, and nevertheless it kept the responsiveness to hydrocarbons. However, the polymers which were used here are rather expensive. Therefore, we tried to find another approach to reinforce the micellar network by using common, highly available polymers. So our approach consists in the reinforcement of micellar network by using hydrophilic polymers which do not interact with the micelles, but which form their own network inside the micellar one. Previously, it was several attempts to add hydrophilic polymers to worm-like surfactant micelles, but the concentration of this added hydrophilic polymer was rather low, and it didn't affect at all the viscosity of worm-like micelles. Here we use rather high concentration of hydrophilic polymer so that the polymer chains are able to entangle with each other and form their own network, which is independent of the micellar network which exists in the solution. Since in our approach, both components are non-interacting or weakly interacting, there is a problem because they can segregate from each other. So that one have one phase composed of polymer and another phase composed of surfactant. To avoid this phase segregation, we proposed to use strongly charged surfactant micelles. These strongly charged micelles make the mixing unfavorable because in this case, most of counter ions would be confined in one phase, which leads to a huge loss of the entropy. Therefore, as soon as we take highly charged micelles, we can avoid this segregation between two weakly interacting components. How we prepared the strongly charged micelles? We prepared them just by mixing of two oppositely charged surfactants, anionic and cationic. As anionic surfactant, we used potassium oleate. It contains rather long hydrophobic tail consisting of 18 carbon atoms. As cationic surfactant, we used N-octyl-trimethylammonium bromide. It contains rather short hydrophobic tail consisting of only 8 carbon atoms. And when we mixed these two surfactants together, we used a high excess of anionic surfactant. As a result, the micelles which were formed were strongly negatively charged. As a polymer, we have chosen polyvinyl alcohol with a rather low molecular weight of 27,000 grams per mole. So our system consisted of two components: strongly negatively charged worm-like micelles of surfactant and uncharged polymer. On this slide, you can see how the addition of polymer affects the rheological properties of the system. On this graph, you can see the dependence of the viscosity on the shear rate. So these are flow curves for these systems. The black curve corresponds to pure surfactant. Orange curve corresponds to pure polymer. When we mixed them together, we obtained this gray curve. So the initial solution of surfactant had the viscosity of 2 Pascal second. The initial solution of polymer had the viscosity of 0.003 Pascal second. When we mixed them, we obtained the viscosity of 600 Pascal second. It means that polymer induces an increase of viscosity by 2.5 orders of magnitude. Simultaneously, it leads to the appearance of a plateau on the dependence of the storage modulus on the frequency. So it indicates that the network is formed. To understand the reasons of the effect of polymer on the rheological properties of worm-like surfactant micelles, we studied the structure of the system by various techniques. First, we studied the microstructure by small angle neutron scattering. These experiments were performed in Russia in Joint Institute for Nuclear Research in Dubna. On the left, you can see the scattering curve for pure surfactant. This is a black curve, and the scattering curve of surfactant plus polymer. This is a red curve. And we can see that at high Q values, they coincide with each other. It means that the local cylindrical structure of micelles is preserved upon addition of polymer. When we look at those curves in so-called Holzer coordinates, we observe that the curve for pure surfactant has a peak. The structure peak characterizes the mean distance between strongly charged micelles. Then we take this system and add their polymer. So we do not change the concentration of micelles, but we observe that the peak is shifted to higher Q values. This means that the distance between the micelles becomes shorter. In other words, when we add polymer without changing the concentration of micelles, we force the micelles to approach closer to each other. What can be the reason of such behavior? The reason of such behavior may be as follows. When we add polymer, tries to expel micelles from some area in the gel. As a result, some polymer-rich and surfactant-rich regions are formed. And as a result of the expulsion of micelles from some area, the average distance between the micelles in the surfactant-rich regions becomes closer. So this shift of the peak indicates the microphase separation in the system with the formation of polymer-rich and surfactant-rich regions. Indeed, when we took cryo-TEM micrographs of this system, we confirmed this suggestion. When we have polymer and worm-like micelles, on the cryo-TEM pictures, we see only worm-like micelles because they are bigger than polymer and they provide higher contrast. So what we see on the picture, we see rather wide area full of worm-like surfactant micelles and some area where there is almost no surfactant micelles. So we observe the picture of microphase separation with some area enriched in surfactant and some area enriched in polymer. It is interesting that surfactant chains, they are supramolecular chains, and their length depends on the concentration of surfactant. And in the surfactant-rich area, we observe rather long worm-like micelles, where in the polymer-rich area, we observe only small, short rod-like micelles. This is indication that in the polymer-rich area, the concentration of surfactant is very low. So the surfactant is unable to form long micelles, but form only short one. What is the reason for such microphase separation? One should say that microphase separation was widely observed in many polymer systems. And always it is due to the competition of some short-range segregation tendency and long-range stabilization tendency. So the short-range segregation tendency tries to form some regions enriched in one of the components, but long-range stabilization tendency prevents the formation of macrophase separation in two separate phases, but just it keeps these small phases of two different components distribution in the whole volume of the system. In our case, the observed microphase separation can result from the competition between short-range segregation of polymer and surfactant components and long-range stabilization, which is due to the presence of large number of counterions, which neutralize the charge of micellar chains. The microdomain structure that propagates through the whole system doesn't impede counterions to travel in most of the volume of the solution. Thereby, it ensures the gain in the translational entropy. At the same time, in this microphase separated system, one can have the local segregation of incompatible polymer and surfactant components that can result in gain in energy. So this as some kind of compromise which allows to gain in energy due to this local segregation, and do not lose a lot of entropy because the counterions still are able to travel in the whole system. Taking into account this structural characteristics, we can suppose two main reasons for the viscosity enhancement observed upon addition of polymer to surfactant solution. The first reason is that we have a local increase of the concentration of polymer in polymer-rich domains and a local increase of the concentration of micelles in micellar-rich domains. And the second reason is that the micelles grow in length because the concentration of surfactant increases. Hopefully, the addition of hydrocarbon leads to very pronounced decrease of the viscosity of the system despite the presence of polymer. This means that the micellar network was destroyed and induced the disruption of the polymer network. So in this system, we have a high increase of the rheological properties, and at the same time, we keep the precious property of micellar network is the destruction and at the addition of hydrocarbon. This was confirmed also by cryothem results, which show that before the contact with oil, we have long micellar chains. After the addition of oil, we have microemulsion droplets. So when micellar network was destroyed upon absorption of hydrocarbon, it leads to the drop of viscosity of the whole system. At the next stage, we try to cross-link the polymeric chains inside this mixed system. For cross-linking, we used so-called dynamic covalent cross-links because we need to preserve the property of destruction of the network and the action of hydrocarbon, and dynamic crosslinks will help us to preserve this property. We took a classical system where polyvinyl alcohol is cross-linked by borate ions. The crosslinks that are formed have the breaking energy of only 25 kilojoule per mole, and such weak crosslinks are reversible. They continuously break and recombine. And here we can see how the polymer cross-linking affects the rheological properties. Here is the dependence of zero shear viscosity on the concentration of polymer. The empty symbols correspond to uncross-linked system. The filled symbols correspond to cross-linking system. Cross-linked system. We see that polymer cross-linking leads to further increase of viscosity and increase of the elastic modulus by 2 more orders of magnitude. So we had 2.5 orders of magnitude increase just upon addition of polymer, and 2 more orders of magnitude increase upon cross-linking of added polymer. And interesting thing is that in the mixed system, the cross-linking starts already at the concentration of polymer 2 weight%, whereas in the absence of surfactant, such gelation concentration is 4 weight%. It means it may indicate the increase of the local concentration of polymer inside this mixed system as a result of microphase separation. The microphase separation was confirmed by cryo-TEM microscopy and by small angle neutron scattering data. From the small angle neutron scattering data, we were able to estimate the volume of each microphase. And you can see that when we add polymer to surfactant, the volume of surfactant microphase decreases, whereas the volume of polymer microphase increases. The most important effect of polymer on the rheological properties was observed at this range of polymer concentration, where the volume of surfactant and polymer phases are close to each other. By cryo-TEM data, it was shown that at these conditions, bicontinuous phases were formed. You can see here the micellar chains aligned along each other and forming such bicontinuous structure. And here, when you do not see the micellar chain, these are the structure of polymer. So the increase of viscosity and the increase of the elastic modulus in the system are due to the microphase separation, which leads to the local concentration of polymer and local concentration of wormlike micelles. This provides a larger number of polymer-polymer contacts for cross-linking and longer micelles with more entanglements. And we were very surprised that we observed the responsiveness to hydrocarbons even in this cross-linked system. Such responsiveness was observed only at polymer concentrations lower than 3 weight%. We suggest that when we take such system and add hydrocarbon, it destroys the micellar networks. Therefore, the microphase separation disappears and the polymer can occupy more volume. But at these conditions, the average concentration of polymer decreases and it becomes lower than the gelation concentration. So in these conditions, the polymer cannot form its own network in the whole volume of the system. So this dynamic crosslinks allowed to keep high responsiveness to hydrocarbons to this system. And finally, let me conclude. In our paper, we have shown that the rheological properties of the systems containing both polymer and wormlike surfactant micelles are vastly superior to those of the components taken separately. At the same time, the systems keep high responsiveness to hydrocarbons inherent to surfactant itself. It makes such systems promising for the application in oil industry. And finally, I would like to acknowledge my colleague, Andrei Shibaev, who performed most of experimental work in this paper. And I would like to thank the financial support of Russian Science Foundation and all of you for your attention. Thank you.
Okay, thank you, Olga.